Hello everyone, welcome to the lecture 21 of the course Diffusion in Solids. So far we have looked in the first couple of weeks about how to solve the diffusion equations more from a continuum approach. The last 2 weeks we saw the atomistic approach. Now this week and the week coming forward, we will look something where the diffusion happens in the presence of a driving force. So when we looked about the tracer diffusion, that there is no concentration gradient, so to say, and therefore the diffusion is more of due to the entropic forces. So now we will see the situation when what is called as interdiffusion, where the two dissimilar metals or alloys come into contact with each other. There is a concentration gradient, and then how we understand that process. In fact, we saw a little bit about diffusion couple when we were solving the diffusion equations, but now the mathematical framework also will change. But before we go to the interdiffusion, it is important to revisit some of the concepts of thermodynamics, basically concerning the free energy versus composition curves and the phase diagrams. So today's lecture is devoted to that, and then we will move forward. So ideal solid solution, GX diagrams, regular solutions, Gibbs phase rule, these are some of the concepts we will cover. So imagine that there are two elements A and B, and you combine XA moles of A and XB moles of B. So before mixing, they are like this, and then if you calculate the overall free energy of this combined system, where there is no interaction between them, it can be simply written as XAGA plus XBGB, where GA and GBs are their individual molar energies. Now, if you mix them at a fixed temperature and pressure, what will happen is that a solid solution would form, and that solid solution will have a free energy different than what is the free energy before mixing. So if we call total free energy of the solid solution as G2, then G2 is equal to G1 plus delta G mix. Now this delta G mix can be further broken down into delta H mix minus T delta S mix, because you might know that free energy consists of enthalpy and the entropy change. So now what is this value of delta G will be determined by the nature of the solution itself, that how is the interaction between the atoms in the solid solution will determine what is the nature of this delta G mix. So graphically this is the situation before the mixing. Simply GA and GB, the G1 is somewhere here on the linear curve. Now let us take the first case where the solution is what we call as an ideal solid solution. Ideal solid solution, what it means is that I will just come to the graph a little later. So in the case of ideal solid solution, the delta H mix is 0, and the configurational entropy or the delta S mix is given by minus R XALN XA plus XBLN XB. Remember what enthalpy of mixing being 0 means is that there is no interaction between A and B. So that means there is no preference that A should sit with B or B should sit with another B atom. It is just completely random solid solution. So in such a case, you have the entropy of mixing given by minus R XALN XA plus XBLN XB, and delta H mix for ideal solid solution is 0. And therefore, you see that the free energy G2 will be equal to XAGA plus XBGB minus RT XALN XA plus XBLN XB. And therefore, if you see, this is the straight line which represents the free energy before mixing, which is XAGA plus XBGB, and then this here is the delta G mix. So therefore, the overall free energy G2 is appears like a curve like this. Remember, if you only plot delta G mix, it will be a symmetric function, but since we add this term, you will have a function like this for G2. And you can see here that we have shown two diagrams here. One is at lower temperature, another is higher temperature. You might be aware and that the free energy is inversely proportional to temperature. So, as you increase the temperature further and further, it goes more negative. So, then if you see one more thing is that you see this expression, for example, XA ln XA plus XB ln XB. These XA and XB are the mole fractions, which is a quantity less than 1. So, therefore, this term is negative and this term is also negative, and therefore, the free energy of mixing of ideal solution is always negative. Okay. So, that is one thing that is important. Any ideal solution, that means if you add even a small amount of XB, you will get a free energy which is negative. So, which is a favorable solid solution formation thermodynamically. Now, another model is what is known as a regular solution model, where the delta H mix is not equal to 0, either heat is released or heat is absorbed. Now, in this case, however, what regular solution assumes though is that the delta H mix that is arising is only due to the bond energies. Okay. So, for this assumption to be valid, it is necessary that volumes of A and B are equal and do not change during the mixing, so that the interatomic distances and bond energies are independent of composition. So, that is what is the assumption. It is known as quasi-chemical model, that delta H mix is only due to the change in the bond energies between the adjacent atoms. So, typically the delta H mix is represented as omega XA XP, where omega is the interaction parameter. I am not going into too much details of how omega is related to bond energies and so on, for which there is a separate thermodynamic course where you can find more details, but for our understanding this is enough. And the delta S mix in the case of regular solution is assumed equal to be the ideal mixing entropy, which is minus R XA ln XA plus XB ln XB. So, therefore, now the delta G mix is equal to omega XA XB plus RT XA ln XA plus XB ln XB. Remember that in the previous slide we saw that for the ideal solid solution, the delta G ideal mix was only this term. Therefore, because this bracket is negative always, the delta G mixing for ideal solid solution is always negative. However, for the regular solution, because now there is a term omega XA XB, it will also depend upon the nature or the value of the omega itself. So, here are the 4 cases that are represented. For example, when omega is less than 0, then this quantity is also negative, this is also negative. So, no matter which temperature you are, you will always have delta G mixing as negative. So, only thing is that if it is a higher temperature, the free energy will be more negative. So, you can see a very deeper curve, whereas here when the temperature is lower, the free energy will tend to become more positive, and therefore, the curve will be little shallower, but it will lie entirely in the negative quadrant. But what happens when the omega is greater than 0? So, now when the omega is greater than 0, there are 2 possibilities. When omega is greater than 0, that means this term is positive term. So, when you are at sufficiently high temperature, that means this term is sufficiently negative. That means that you can see here that this is the delta H mix, which is positive because omega is positive. But if the temperature is high, this term is highly negative. As a result, you will get delta G mix entirely negative. But if we lower the temperature such that at some compositions this omega XA XB term or delta H mix term is able to overcome the T delta S term, then you will have a situation like this, where for certain composition range, the delta G mix becomes positive. So, what it means is that in this composition range from this point here to this point here, the delta G mix is positive. If delta G mix is positive, that means the free energy change is positive, which is not a favorable thermodynamic condition. So, therefore, if you let us say mix A and B, where the omega is positive and you have mixed at this lower temperature, then throughout the composition you are not going to get a single phase regime. There is a region where a single phase is not stable, and later we will see that it actually prefers then to have as a two phase mixture. Now, let me define one more quantity for you, which is known as a chemical potential. So, it is often important to understand that how the total free energy of a system changes when I add a small amount of one of the components. Okay, that is known as the chemical potential. Okay. So, it is equal to the change in total free energy of the system on addition of DNA moles of A at constant temperature and pressure. Okay. So, it is an important quantity to know that especially when you have more than one component system, then which of the element is impacting the free energy to the maximum extent. Okay. I will just give you another analogy in your everyday life. For example, when you make a food, if you add a little bit extra chili or a masala, then okay, it is still edible. But if you add extra salt, then it becomes very difficult to eat. So, that means the impact that an X amount of salt will have on your food versus some other spices will be different. Similarly, in a solid solution or even in any type of solution, this is important to know that how much a small quantity if I add of each component, how much the free energy is going to change. So, that is defined as the chemical potential. So, dG bar is equal to mu A into dNA. Mu A is also referred to as the partial molar free energy of A or chemical potential of A in the particular phase. Remember, chemical potential is always defined for a particular component in a particular phase. Okay. It will be more clear. So, if for example, you might have known or heard about steel, which has a pearlitic structure alpha and Fe3C. Now, if I want to define chemical potential, I have to say chemical potential of carbon in alpha, chemical potential of carbon in Fe3C. So, I need to specify the phase also. I cannot say just the chemical potential of A in steel, that is incomplete. So, if the free energy changes by 1 mole, then one can write G is equal to mu A x A plus mu B x B. You can try this out. There is a separate relation. Mu A is equal to G A plus R T ln x A, mu B is equal to G B plus R T ln x B. What essentially it means is that mu A is dependent upon the composition. So, if more is the element A, the higher will be the mu A. So, this you can try out for yourself how to prove it. Graphically, how you can calculate mu A is also important. So, here if you plot this curve G, okay, then at any point if you draw the tangent, so this CD is the tangent, then wherever this tangent meets the intercept or wherever it meets the A axis, that point will be as given as mu A. Wherever it meets B axis, this will be given as mu B. So, remember this construction, this is very important in our next lecture also. So, wherever you draw a tangent to the free energy curve, remember it is a free energy, not the change in free energy. So, free energy curve, wherever you draw a tangent, where when the tangent intersects the A axis, that point gives the chemical potential of A in this particular phase for which you have drawn the free energy. Similarly, wherever it intersects B axis, it gives the chemical potential of B in this particular phase. So, this graphical proof is something interesting you can try out for yourself. Now, let me tell you, so far we saw a single phase or single free energy curve, but in quite a lot of situation you have where two phases are existing together. I just gave the example of steel where alpha and Fe3C exist together. Several examples can be given where more than one phases are in equilibrium. So, in such a case, how do we understand? So, in that case, for example, if you have a situation where alpha and beta are existing together, the free energy diagram would look something like this. So, you have a G of alpha and G of beta, and this is the composition until which. So, you see here. So, if you compare, see ultimately how do we understand the competition between phases? So, if there are two phases alpha and beta which can exist at a given temperature, then whichever the phase has the lowest free energy will be the one which exists. Remember, this is drawn at a constant temperature. So, now if you compare the compositions between this point A to this point C alpha equilibrium, clearly the G alpha has the lower values than the G beta curve here. Similarly, from C beta equilibrium to this point, you have the G beta which has the lowest values. What happens in between though? Okay, what happens in between? So, in between what happens is also interesting. So, if before we go to there, if I lower the temperature now, then what will happen is that the curves will shift upwards, and therefore, these composition also changes. So, in between actually it exists as a mixture of alpha and beta. Okay. So, and this tangent, common tangent at any point on the common tangent is the free energy of a mixture of alpha and beta. So, if I lower the temperature, then all the curves will shift up, and therefore, the equilibrium composition also will change. Okay. Now, you have alpha stable up to a higher composition range. So, this is also reflected in the phase diagram, and therefore, there is always a one-to-one correlation between the G X curves and the phase diagrams. Additionally, what is also interesting for us to note is that just now in the previous slide we said that if you draw a common tangent, then wherever it intersects the A axis, it will give the chemical potential of A in that particular phase. Now, you observe this clearly carefully, this region where two phases are existing. So, this tangent, this is a common tangent to alpha and beta curve. Now, this tangent, because it is common, now when it intersects A axis, this point not only gives the mu A in alpha, but it also will give the mu A in beta, because this is a tangent to the beta curve also, this is a tangent to the alpha curve also. So, wherever it intersects the A axis, it represents not only mu A alpha, but also mu A beta. Similarly, in on the other side, you will have mu B beta as well as mu B alpha. So, what it tells us is that at equilibrium, when the two phases are in equilibrium, then the chemical potential of all the components in each of the phases are equal. So, mu A alpha is equal to mu A beta. If there were three phases, then it will be equal to mu A gamma or mu A delta, depending on how many phases are there. Similarly, mu B alpha, mu B beta, mu B gamma all will be equal. Again, just to clarify, we are not saying that mu A alpha and mu A beta are equal, or mu A B mu A in alpha and mu B in alpha are equal, but mu A in alpha, mu B in beta, mu A in beta, mu A in gamma, and so on are equal. So, that is the criteria for the equilibrium. Now, this equilibrium criteria also gives rise to what is known as the Gibbs phase rule, which says that the degrees of freedom f, which is the minimum number of independent variables that must be fixed to understand the system fully. So, this f is equal to total number of variables minus the number of equations connecting them. That means, it basically measures how many variables you can vary independently. So, if there are p phases, let us say in a equilibrium in a C component system at temperature T and pressure P, then composition variables are C minus 1 for each phase. Why C minus 1? Because there are all the composition, let us say if you are talking about mole fractions, XA plus XB plus XC equal to 1. So, therefore, it is sufficient to only define for C minus 1 component. So, the composition variables are C minus 1 for each phase. Therefore, for P phases it will be P into C minus 1. Then the total number of variables are P into C minus 1 plus 2. The two variables are pressure and temperature. So, these are the thermodynamic variables. The number of equations connecting them are P minus 1 for each component. What are these P minus 1 equation is what we just saw in the previous slide, that mu A alpha is equal to mu A beta is equal to mu A and gamma and so on. Similarly, mu B alpha, mu B beta, mu B gamma are equal, so on. So, you can see that if there are P phases, then there are P minus 1 equations for each component. So, therefore, the total number of equations connecting are C into P minus 1. So, therefore, the degree of freedom is equal to P into C minus 1 plus 2 minus C into P minus 1. If you rearrange this, then you get F is equal to C minus P plus 2. This is your Gibbs phase rule. And if the pressure is constant, which is the case for several metallurgical processes, then you will get F is equal to C minus P plus 1, because instead of 2 now variable is only 1. This is known as condensed phase rule. Now, let me show you a couple of examples of GX curves of different types of phase diagrams. So, first is the isomorphous system. So, let us say you want to draw the phase diagram is here, and you want to draw the G versus X curve at T2. You can see that up to this point there is a single phase alpha, then alpha plus L, and then followed by liquid. So, this is how the free energy curve looks like, and you draw a common tangent here. So, this is the C alpha equilibrium and C liquid equilibrium. So, these are the points represented on the phase diagram also. So, you can clearly see from here A to C alpha equilibrium, G is lower than G alpha is lower than GL, therefore, alpha is stable. Similarly, here GL is lower than G alpha, so liquid is stable. In between, you have the possibility of drawing the common tangent, and therefore, you have a two phase mixture which is stable. That means, in this region neither single phase alpha nor single phase liquid will give you the lowest free energy, but a mixture of alpha and liquid has the lowest free energy. Similarly, you can also try out at other temperatures which are like melting point of B. At the melting point, the free energy of liquid and alpha will coincide with each other. Then you can also try at this temperature T3, where simply the alpha phase will have the lowest free energy. As an activity question, you can try a copper and nickel phase diagram and draw the GX curves at the melting point of nickel and atmospheric pressure. Remember, G versus X is always drawn at a constant temperature and pressure. Now, what happens when there is a miscibility gap? So, miscibility gap is also quite common in several systems, where you have let us say alpha is existing on most of the composition range, but for certain temperature and composition this alpha is not stable as a single phase, but it splits as alpha dash plus alpha double dash. And this happens usually when the omega is slightly positive at lower temperatures, and A and B, even though there is a miscibility gap, they tend to have a similar crystal structure. Copper nickel, in fact, when you see the phase diagram, you will see that there is a miscibility gap, and usually alpha prime and alpha double prime, they have a similar crystal structure as alpha. So, there is only a gap in miscibility. It is not that these systems are completely immiscible or so on. There is a gap at certain temperatures and pressure, why the miscibility, at which the single phase alpha is not stable. So, as I said that you get miscibility gap under this condition usually. Complete miscibility in liquid, omega greater than 0, and A and B usually have the similar structure. So, here if you want to try at T1, it is simple. You have liquid, and then alpha is all the compositions above the liquid in the free energy curve. When you want to draw at T2, T2 is an interesting exercise for you. You should be able to see the two-phase regions. Okay, so here you see that here also there is a two-phase region, and here also there is a two-phase region. So, when you draw the GX curve, it should be something like this, so that you have one common tangent here and one common tangent here. So, there are 4 points here, the intersection points for alpha and liquid free energy curves, or rather intersection points are 2, but there are 4 points where the common tangents can be drawn. So, this is A, B, and C and D. So, these are the A, B, C, D reflected here. So, you can see up to A there is only single phase alpha, then again between B and C, if you notice that single phase liquid is stable. So, there is always one-to-one relation between the phase diagram and the free energy curves. Now, when we draw for the miscibility gap, then the miscibility gap you draw something like this. So, the liquid free energy curve is L, liquid is not there anywhere. So, it will be way above the alpha free energy curve. But alpha, remember one thing, that when we draw the free energy curve, we draw the free energy curve for a particular crystal structure. So, as I said that in this case alpha prime and alpha double prime, they both have a same crystal structure. So, therefore, we are not going to draw different free energy curves for different like alpha prime or alpha double prime. There is a single free energy curve which have the nature like this. This is similar to what we saw when there is a regular solution with certain omega positive at a lower temperatures. That is why you will see that the miscibility gap occurs always at the lower temperatures. So, here now this is how the curve looks like, and therefore, you have the situation where this point here is E, which is represented by this point here in the free energy curve, where the free energy starts becoming positive, and here it is F, where again the single phase is stable. So, this region is clearly reflected in this free energy curve also. Okay. So, this is an example just to show you how we can draw the free energy curves for a more complicated phase diagrams, also like iron Fe3C. So, typically if you see that iron Fe3C, there are possibility of alpha, delta, Fe3C, gamma liquid phase. You put all these curves in the free energy diagrams. You also notice that because alpha and delta are only stable for certain small carbon percentage, therefore, we have drawn them like this. So, that after a certain carbon percentage, they are not stable as a single phase because the free energy is quite high. Similarly, Fe3C, if you look at Fe3C exists only at 6.67% carbon, and therefore, its free energy curve is extremely steep. So, you will see that only at this point it is lower, and then it suddenly increases. So, if you want to draw at T1, you have to see that there are two, there is one single phase region of gamma which is here, which is lower than all the free energy. Then there is a single phase region of liquid, and in between there is a gamma plus liquid and liquid plus Fe3C. So, you have this the common tangent constructions. Similarly, at T2, you can draw T2, there is no liquid, but there is a common tangent or the two-phase mixture of gamma plus Fe3C. So, now at T2, what also will change is that because if you see at T2 carefully, there is a small region where alpha is stable. So, that means this alpha free energy curve has come down. Then there is gamma, liquid, and Fe3C. So, then the common tangent constructions can be made like that. So, this is the region where alpha plus gamma are stable. This is the region where gamma plus Fe3C are stable. Now, before we end today's lecture, here's an interesting activity question for you. So, let's say Bhavna came across an advertisement in this newspaper. It was about a certain company who claims that they make articles containing 100% of silver. Now, Bhavna, being a TA for this course, understands the thermodynamics very well, and she writes a letter to the company that it is not thermodynamically possible to obtain 100% of any metal, so 100% of silver. Now, she is waiting for the reply. What do you guys think? Is she correct that it is not possible thermodynamically to obtain 100% Ag? Feel free to post your answers in the forum. Okay, so then next week or next lecture rather, we'll talk about the driving forces for this process of interdiffusion.